Welcome back to Topics in Topology. Today we will calculate homology using matrices. I did want to say one thing before we get started. I'm a bit behind on updating our website. I will do that this weekend. I injured my right arm and I found typing a bit difficult, but we will still get things updated this weekend. I typed part of my thesis with my feet, drew some of the pictures, so I can definitely get things updated, although I think I'll actually use my hands over the weekend. So look for, all the lectures are actually recorded and posted on YouTube. I will add links to the course website as well as links to supplementary reading, and homework will later be posted as well. Any questions on that? Okay, so now I'll put, it is record, so I think we're good, except for I unrecorded. Okay. We're good. So again, welcome to our Topics in Topology, calculating homology using matrices. That's what we'll do today. On Monday, I will give my all-time favorite lecture. Okay, I haven't actually given that lecture yet, but it's a lecture that has the potential to change your life. Okay, it's a very slim potential, but you could make a major discovery as the result. And one of the reasons I'm so confident about this lecture is, well, it's based upon a lecture by Rob Greist. So Carlson and Greist organized a short course on applied algebraic topology in 2009. All the videos related to this lecture are available on the IMA website. If you go to that 2009 short course, there'll be links to the schedule and links to all of the material from that short course. They only had 2 weeks. So I am going a little bit slower than they did because I have a full semester, and I'll put my own twist on it. So even if I recommend his lecture, you should listen to mine as well because I'll put my own twist on it. So come on Monday to the lecture where you could make a major discovery, not during the lecture, but it might give you some good ideas, I am hoping. Okay. So let's now go back to computing homology. So just to review what we did last time, we counted the number of connected components using the zeroth homology, so using H0. And to do that, we basically said we will use the vertices to represent the components. So V1 could represent all the other vertices that it's connected to. V4 could represent all the other vertices it's connected to. And so we can use the vertices to represent the components. And then we had relations. So these were our generators right here. But then we had relations based upon, so we had relations, well, all the way out to here based upon, since we had an edge connecting V1 and V2, we know that they are in the same component, so we could use that relationship to say that V1 equals to V2 mod 2. And so thus we don't need V2 is in the same component, so I'll remove that. I've now used this relationship, and now I'm down to only 5 generators and 4 relators. And we can continue doing that. I just need to remember that V1 equals to V2, so wherever I have a V2, I can now put a V1, and I can use that to get rid of V3 here, getting rid of that relation in that generator. And we continue doing that until we were down to just V2 using all of these. And this one, since V4 was the same thing as V5, we just repeated this equation, so that didn't give us anything new, and so we got down to simplifying to this. So that is one way to calculate the zeroth homology, is just take your generators, and for the zeroth homology, the generators will be all your vertices, and your relators will just be the boundary of all your edges. We just take the boundary of all our edges, and that's where our 5 relators came from. And then we can simplify that. What we have at the moment is a group presentation. It is well known that dealing with an arbitrary group presentation in algebra is messy and difficult and not easy. Comparing two group presentations is not always obvious if you actually can get down to the same thing. However, what we're doing will actually be very simple. So we will actually be able to work very nicely with our group presentations. And there's still the question as to the way I did my relationship. I got V1 to represent my component and V2 to represent the other component. If somebody else does it and they label things differently, they might get V2 to represent the component, this component, and V6 to represent the other component. So the representations actually might be different, but one can still have a very nice, simple algorithm, and that simple algorithm is to use matrices. So we can keep things nice and organized. Hopefully you remember working in linear algebra that as long as you did your row operations nice and organized, you could very quickly solve a large system of linear equations. And that's pretty much what we have. What we have here is the equation V1 plus V2 equals to 0. So I've got V1 plus V2 equals to 0. I also have V4 plus V6 equals to 0, so V4 plus V6, that's my last equation, as well as all the intermediate equations. We, however, want to start off with actually the transpose. So we're going to take the transpose of this matrix. And the reason we want to take the transpose of this matrix is because we want to have the matrix represent this nice linear map. So remember, to calculate the homology, to calculate what was in our connected components, we need to know the boundaries of these things. And then once we knew the boundary, we extend it to C1, which was arbitrary linear combinations of our E sub I, so all linear combinations of our E sub I, that created our C1. And we extended this map, so if we knew how it acted, how our boundary map acted on our E sub I's, we extended it to all of C1 linearly. That means that this thing is a linear map. And we have a nice linear map between finite dimensional vector spaces. C1 was generated by our 5 edges right here. So I can use if I use column vectors, a 5 by 1 matrix, a column vector to represent my 5-dimensional space, which is generated by these 5 elements. My C0 has 6 generators, these 6 vertices right here. So I can use a 6 by 1 column vector to represent, an element in C0. And to go from a 5-dimensional space to a 6-dimensional space, well, I will want a 6 by 5 matrix so that I can then multiply it by a 5 by 1 matrix to get out a 6 by 1 column vector. And so we will, since this is a nice linear map between finite dimensional vector spaces, we can do a nice matrix to represent this linear map. And that is just the transpose on the preceding page, where since the boundary of V1, V2, so that was my edge E1, so I can either use E2 or I can use V2, V3. So a pair of vertices will represent an edge. And the boundary of E1 was V1, V2. The boundary of E2 was V2, V3. If I've got V4, V5, then I will have a 1 in the V4 and 1 in the V5 row underneath the V4, V5 column. And if we take a look at it as a map, well, first, that's since we do have a 5-dimensional, so our basis for C1 are 1-dimensional complexes, which will just be linear combination of our 1 simplices, our edges. We'll just go ahead and use this 5 by 1 matrix, where if we've got E1, a 1 is in the first spot, E2, a 1 is in the second spot, EI, a 1 would be in the ith spot. And so we can use these 5 vectors to represent our edges. So we can use any symbols we want. I like these symbols. They work very nicely for matrices. For our vertices, because we've got 6 of them, we'll now have a 6 by 1 matrix, so 6 rows, 1 column, with again, if I've got VI, a 1 in the ith column, zeros elsewhere. Well, I can now take, so this, remember, was my edge E1. The boundary of my edge E1 is V1 plus V2, so that's V1 plus V2, because I've got a 1 for my V1 plus a 1 for my V2. And my matrix here is the boundary map that sends E1 to V1 plus V2. So if I multiply these two maps together, you can see that we will get, this times this gives me 1, this times this gives me 1, and every place else I will get zeros. So multiplying them out gives me exactly what I want. We can see that in terms of the picture as well. My boundary of E1 should be V1 plus V2. And since I'm doing standard matrix multiplication, and I'm multiplying by E1, where I've got a 1 here and zeros elsewhere, I am picking up the first column, which we said represented the boundary of E1. I can similarly do that for E2. 2 in the second row means I'll pick up the second column, and that is exactly where my boundary came from. So that's why my second column has that the boundary is V2 plus V3. And we can do that for E3, E4, and E5. And we then extend linearly. So if I want to take an arbitrary sum, so if I take an arbitrary element in C1, it will be some linear combination of my E sub i's. And I'll remember each of my E sub i's was, this thing with a bunch of zeros and a 1 in a spot. If I multiply by N1 or Ni, I will just replace the ith spot with Ni, so I'll get N1, N2 to N5. And so now we'll be representing an element, an arbitrary element, by this 5 by 1 matrix of just integer coefficients. Well, our integers, because we're working over Z mod 2, will be either 0 or 1, but that's what we'll have. And so I can go ahead and now this is an arbitrary element, so this thing is in C1, and I can then multiply the two matrices to get out an element, so this would now be an element in my C0. I've now taken the boundary of this. So you can think about this multiplication in two ways. If you remember your matrix partitioning, I just partitioned this matrix, and so I can do N1 times this column, so N1 times this column, N2 times that column, etc., and I get this. And we also know that the boundary of N1 times E1 is N1 times the boundary of E1. N2 plus E2 is N times the boundary of E2. So if you check the algebra, this all works out nicely. So in other words, remember I wanted to look at the image. I was interested in the image of this map. Well, what is the image of this map? I'm getting all linear combinations of the columns. So the image of my boundary map is the column space of this. It's just all linear combinations. This right here is my image. And that is identical to the column space, all linear combinations of the columns. Well, we wanted to simplify our image space. Remember, we originally had 5 relators, Z1 plus Z2, Z2 plus Z3, etc. Plus we had this extra one that we didn't need. Well, we can do column operations to get rid of the extra generators. And so if I do a column operation on this, first off, before I do the column operation, we can see again our matrix corresponding to our picture. But to simplify things, I'm going to go back to using E1 and E2 because it's smaller. So we'll use E1 and E2 for our edges. And now I'm going to do the column operation, where in this particular case, I'll go ahead and do E3 plus E5. So, or in other words, I'm doing column 3 plus column 5 and putting it into column 5. So that's what I'll do is add these two columns to get this thing to be 0 right here, standard column operations. Well, if I add these two columns, I'm doing 1 plus 1, so I will, be changing this 1, adding these two columns, I get 1 plus 1, and we all know that 1 plus 1 equals to 0, mod 2, and so this will be replaced by a 0. When I add 1 plus 1, I'll get a 1, and so I will get when I do column 3 plus column 5 and put it into column 5, I'll get 0, 0, 1. But I'm also going to replace this thing, my E3 plus E5. I'll put that into my 5th spot. I'll put that into my 5th spot as well. And so what I get is we had our addition that we did before, so on our previous thing. So let me go back to the previous page. We had a 0, 0, 0, 0, 0, 1, 1. So we had that there. And now when I take a look at here, what did I just do? I did E3 plus E5. Well, what is the boundary of E3 plus E5? What is the boundary of this? What is that boundary? Now, it's V5 plus V6. So my boundary is V5 plus V6. So when I do my column operations, I am getting the boundary here of the sum of my E3 plus E5. In other words, what I've just done is a change of basis. So before I had my relators E1 through E5, now I'm going to have my relators corresponding to E1, E2, E3, E4, and the sum E3 plus E5. So I'll have those equations instead. I've done a change of basis. And now with this change of basis, it's kind of nice because I can now see that if I compare this column and this column, well, they're going to give me the same relation. So whether I talk about the boundary of this edge or whether I talk about the boundary of this sum of the two edges, I get the same boundary, so it's the same relation. And so I can see that if I now add these two columns, we know again 1 plus 1 is 0, mod 2, if I add these two columns and put it into here. So now I will do column 4 plus column 5 into column 5. But at the same time, I will do my E4 plus my E3 plus E5. So I'll do another change of basis here as well. So when I add these things here, I'll not only get zeros here, I'm also going to be adding the E4 right there. So we now have this. And well, what is the boundary of E3 plus E4 plus E5? What is the boundary of this? It's 0, which is good because we now have that its boundary is 0. So we can do a change of basis so that we can see what is happening with our relators. And we now can see in our first 4 columns, they're all linearly independent. So these columns here are linearly independent, so I can't really simplify anymore, or I can't reduce the dimension. That I will have 4 relators. So I will have 4 relators. Since these things are linearly independent, I will need all those relators, and so we will have 4 relators in our group presentation. Any questions so far? Okay. So we can go ahead now and take a look at our 5 relators. But remember, we didn't need this one, and so in reality, we're going to be left with our 4 relators. So I think that's yes. So let's, yeah. So we just went back to, so because of this column here, we just needed our 4 relators, and we're in good shape. Mostly. We then remember, one other thing is we're working over Z mod 2 coefficients. We could work using integer coefficients, so I could talk about 5v1 or real coefficients, pi times v1. Fractions would be fine if you want to work over the rational, so 3/2 v1 is perfectly fine. If you work over arbitrary coefficients, then we need to have our edges need to be oriented. So I should be able to draw here as well. And so we're going to have an orientation on this thing. The pen's not very well calibrated, but we have to have an orientation. And now the boundary of E1, because E1 points from V1 to V2, its boundary will be V2 minus V1. So we have V2 minus V1 for the boundary of E1, V3 minus V2 because it points to V3 starting from V2, so the starting point gets the negative sign. So you can still do everything with arbitrary coefficients, that's perfectly fine, and everything works pretty much the same way. So if I now do my column operations, I just went ahead and added, so if I go back here, let's just add E3 plus E4 plus E5. If I add all three of these columns and put them into this column, I will get, adding these, I get 0, 0, 0. And I also get E3 plus E4 plus E5. And so the operation is basically the same. So you can do arbitrary coefficients, and that works just as well. Well, except if you're working over, if you care about speed, I can do 1 plus 1 is 0 a lot faster than a computer can do pi plus, E equal to something. And worse yet, if you work over the integers, you can't divide. And this is a very simple example, so we haven't, gotten any, ugly coefficients. But if you work over the integers, you might have a row that starts with a 3 and another row that starts with a 2. 1/2 is not an integer, 1/3 is not an integer, so you can't use division. So when you work over the integers, the computation goes up a lot. It takes a lot more work to work over the integers since you're not allowed to divide. So it's a lot faster over Z mod 2, and in many cases, we only need Z mod 2. For H0, Z mod 2 is perfectly good. But you can sometimes lose some information, so sometimes you might want to work over arbitrary coefficients. If it's a field where you have division, that's better than if you don't have division, but one can still do it. Okay. So let's go back to our unoriented ones. We can also do row operations, but notice that there is a difference when I do row operations. So when I do row operations, so suppose I now do, let me see if I can write with this mouse, row 1 plus row 2, and put that into row 2. So I'm putting that into row 2. It's important that we're putting it into row 2. So I just do 1 plus 1, we know is 0, and I put that into row 2, and that was the only thing that wasn't 0 up here, so we get this matrix up here. Note, however, that now when I do my change of basis, I still want that the boundary of E1, I want that to represent V1 plus V2. Well, I only have a 1 in the first spot. So that means I need my first row to now represent V1 plus V2. So when I do a row operation of row 1 plus row 2 and put it into row 2, I change my row 1. Before, when I did column 3 plus column 4 plus column 5 and put it into column 5, I changed my column 5 basis representative. Now, even though I'm putting it into row 2, I don't change my basis in row 2. I keep that the same. I change my basis in row 1. So even though, that's why I wanted to write down this 2 right here. This thing is really badly calibrated, so circling this 2 will be hard. But that's why I wanted that 2 there, is we're not putting it into row 2. We're putting it into our row 1. Let's get back to our row operations, and so we wanted our boundary of E1 to be V1 plus V2, and so we did our change of basis into row 1 instead. Any questions in the meantime? Should have asked questions while we're having, others. And we can do lots of row operations, so we do lots of row operations. And so now we have the simplest matrix. Well, I could have done another row operation switching these two, but we can see now that we have our generators are E1, E2, E3, and E4, and that those boundaries are V1, V2, V2, V3, V4, V5, and V5, V6. And so we can see that in this matrix after we do row operations. Row operations, however, are not as important as column operations, because I could have seen in this matrix that these are, again, my important columns, and I can see that the boundary is V1 plus V2, V2 plus V3, etc. So I could have seen that in there as well. So the most important thing is to do the column operations. Row operations are often optional. So here, if we use our arbitrary coefficients, if I now have my boundary of E1 is V2 minus V1, so I've got a minus 1, 1, I will now do row 1 plus row 2 and replace row 2. So I add these things, I get a nice 0 there. I again change my row 1, not my row 2 generator, but now I want the boundary of E1 to be V2 minus V1. In other words, I want it to be minus 1 times V2 V1 minus V2. So this is the correct generator here. So even though I had a plus sign right here, I need a minus sign over there. So when you do work over arbitrary coefficients, you do have to keep signs in mind. And when you do row operations, that definitely has an effect. Column operations, we were fine, but for row operations, we do have that minus sign. So we have now calculated our relators nicely, so we know everything about our relators and how to simplify them using a matrix, but we also need to figure out our generators. Well, for this particular case, our generators are everything, but let's do it in matrix form anyway. So remember, our generators was actually the kernel of our next map. So we had looked at the image, so our B naught came from the image of boundary 1. But now we wanted to take a look at the kernel of the next map down, boundary 0. And so the kernel is the thing that sends everything to 0. Well, because in this case, the boundary of a vertex is 0, everything gets sent to 0, so thus we know all our generators will be in the kernel. But I want to represent this in terms of a matrix. We already represented this one in a matrix. Now let's represent this one in a matrix. This one over here, our boundary 1, was a nice 6 by 5 matrix. So I could take a 5-dimensional object in C1, multiply it by a matrix, and get my 6-dimensional matrix, right? My 6-dimensional column vector out here after multiplication. Well, now in my boundary naught, I'm going from a 6 by 1 column vector to 0, which is a 1 by 1 number. And so we can now multiply by a matrix that is now a 1 by 6. And being what matrix is going to send, what 1 by 6 matrix will send everything to 0. So I need an example of a 1 by 6 matrix that sends everything to 0. Well, there's only one. It's the 1 by 6 matrix consisting of all zeros. So in this case, our stuff is pretty easy. Our null space is easy to see. We don't have any leading entries, so our null space is everything. And so we do have our kernel. So we now know our generators from our Z naught, as well as our relators from our B naught. We simplified this one using matrices. This one didn't need any simplification, but we could have. So just to refresh what we've done, we've talked about our zeroth homology is the kernel of our boundary mod the image of the preceding boundary. So it was the kernel, everything that got sent to 0, which was all our vertices. Modding out by our relators was our edges. So if there was an edge, we wanted to mod out by that, get rid of any edges that were connected, because we just wanted the number of components. We saw that that was equivalent if I represent my boundary naught by a matrix M naught and my boundary 1 by a matrix M1, then we saw this was equivalent to doing the null space of M naught modded out by the column space of M1. Thus, if I want to do the rank, since I'm working over Z mod 2, I won't ever have torsion. So if I just want to know my rank, I can just take the rank of Z naught. Well, we had 6 vertices. I had 4 relators, so 4 relators. And so my rank of H naught will be 2. Often you just want to know the number of components. If you want to know the number of components, you don't actually have to fully compute your H naught. All you need to know is the rank of these two things. And if you subtract the 2, because I've got my generators, but I have 4 linearly independent relators, which I can use to get rid of 4 generators. 6 generators minus getting rid of 4 of them leaves me with 2. And so I can find out that I will have 2 components. And so my H naught will be 2 copies of Z mod 2. So we'll have 2 copies of Z mod 2 via that. So, Z naught, our null space, we can see right here, has rank 6 because there are 6 zeros. And we can see the rank of this thing is 4 because we've got 4 linearly independent columns. Any questions about that? Well, we can generalize this. Oh, so this is just saying the same thing in terms of, in case you've forgotten the pictures, it's nice to see the pictures from time to time. But now let's generalize this. We can do this in any dimension. So instead of just, we focused on this right here to count the number of connected components. Well, I can count the number of one-dimensional holes, or I can count higher dimensional holes using the same procedure, but use the higher dimensional maps instead. So Hn is defined to be the kernel of boundary n plus 1, so everything in here that gets sent to 0. So that will be called a cycle. So another way to say that is a cycle. And then we mod out by the image over here. So we mod out by the image of boundary n plus 1. We will call that the boundary. Now, there's one detail that I'm not going to get into today, but we will discuss a little bit more. But notice that if I'm going to take cycles mod boundaries, I better have that my boundary is actually a cycle. In other words, if I'm going to take the group, the kernel, the things that get sent to 0, well, everything here had better get sent to 0 as well. So if I take the boundary of a boundary had better be 0. Well, the boundary will always have boundary 0. So the boundary of a boundary will be 0. So we are okay. So if I do this thing, I will get the 0 map. And so algebraically, this will work. We will discuss that more later, but we're good. So everything does generalize nicely. We can do kernel mod image. That'll be the same thing. The kernel, remember, was just the null space of this map right here. Mod the column space of this map right there. That was our image. And we get the same sort of thing. If I just want to count the number of holes, I can just do my rank of this thing minus the rank of that and just subtract them two out to find out the number of holes. So let's go ahead and take a look at a one-dimensional, at the one-dimensional holes. So now instead of taking a look at going towards 0, so we're not going to do this now. We're going to take a look at this one, where we are now going to take a look at the boundaries of triangles going to edges, and then the boundary of an edge going to vertices, and that's the part of the map that we will look at. So we still have the kernel of this map, whatever gets sent to 0, mod the image of this map, our null space, mod our column space. But we don't actually need pictures. So in terms of pictures, I can, is this my, yeah. So we can just use our matrix. We already have the matrix. Remember, we just wanted to know the null space of M1. We'll look at the pictures later at the end, but we can just do it with our matrix. We know that M1 represented this map, and right now I want to know what is the null space. What gets sent to 0? Well, I can do column operations because I can do a change of basis. So I can do a change of basis, do column operations, and work with this one instead. I will get the same null space. So I just need to know the null space. Working with a simpler matrix works. And since we've already done the column operations, let's work with the simpler matrix. So I want to know what's my null space. I want to know when I multiply these two things, what gets sent to a whole bunch of zeros. Well, these 4 columns, are all linearly independent. So if I do n1 plus n2 plus, n1 times column 1 plus n2 times column 2, etc., up to column 4, if I'm going to get a bunch of zeros using some linearly independent columns, these are going to have to be 0. So in my null space, these will all have to be 0. This, however, can be anything it wants. If I multiply, this row by this, to get 0 out, n1 must be 0. n2 can be anything for this one, but for the next one, I'll get it to be 0. But n5, when I multiply this times that, I'll be getting 0. So no matter what n5 is. So in other words, n5 is, this last entry will generate my null space. So my null space will be generated by, it'll be all things of the form where this can be anything whatsoever. So this will be my null space. So we've already calculated our null space when we calculated our column space in the preceding example. So we can use the fact that we already have this matrix to calculate our null space and have a nice null space. Any questions on that? And we also know that our null space, that this has dimension equal to 1 now, and we can see that we've got 4 leading columns plus 1 free, and so our dimension is 1 for our null space. So, and we can also see that our null space is going to be generated by the boundary of if I take a look at the things, take a look at the things that go to 0, it will be generated by this element right here. So this was the term that corresponded to what got sent to 0. These things, we had to have these things being 0 right here. So it was only this last column, and so I know that is what gets sent to 0. I know this thing gets sent to 0. So I know that my null space is now generated by, in here, by E3 plus E4 plus E5. So I know exactly what my null space is. We now want to calculate our column space. For our column space, we want the image of boundary 2. We want the image of boundary 2. So thus, I have now my boundary 2 map. My boundary 2 map goes from my generators here. Well, I only have one face. I only have one 2-dimensional generator. The only 2-dimensional generator is this face right here, which is generated by V4, V5, V6. And so I've got my 2 simplex, so that is my face right there, my 2 simplex. I can write, my edges E1, E2, etc., but it's nice to see them in terms of this format, because now if I want to calculate the boundary of this, well, notice the boundary is if I remove V4, then my boundary is going to be V5 plus V6. If I remove V6, my boundary is V4 plus V5. If I remove V5, then my boundary is V4 plus V6. So by removing, if I remove one vertex at a time, remove V4, I'm left with this edge. Remove V5, I'm left with that edge. Remove V6, I'm left with this edge. And so we can see that if I remove one vertex at a time, that tells me exactly where to put my ones. I mention this because this works with any dimension. So even if you're working with a 10-dimensional or a 100-dimensional object, well, if you're working with, so with this 2-dimensional object, I needed 3 vertices. So with a 100-dimensional object, I need 101 vertices. So its boundary, just remove one vertex at a time from that 101 list, and you'll get the boundary. So we have our boundary right here. Usually when you look for holes, you're usually looking for holes of a smaller dimension, but one could do higher dimensions as well. So we have this thing right here where our boundary is, map is represented by 0, 0, 1, 1, 1, and so that's our boundary map. Any questions? So we can see that the image of boundary 2 is just the column space. Well, my column space is the boundary, you know, it's just, so the image of this will be the boundary of my face V4, V5, V6. And I can see that that will be the sum of these two, identical to what we did before when we had the boundary of an edge. Now we just have the boundary of a triangle. It's going to be generated by this. And remember, this one was E3 through E5 right here. So we got that it's generated by this here. We can now mod out. This was my null space. This was my column space. Everything canceled out. And so we just get 0 because we're working over, you can use the additive identity or the multiplicative identity. I like the additive identity because we've got a group here, so we'll use 0. So our group is just a 0 group. Our rank is 0. So we got rid of this generator, gets rid of that generator, and so we just have 0. In other words, if I take now and take a look at my picture, do I have any cycles? There are no cycles. I have 0 cycles. So that's what I have here is 0 cycles. And so H1 here equals to 0. We have no copies of Z2 because we have no cycles. And you can go back and take a look at the matrices to see that it does make sense in terms of the pictures. So we can see it does make sense in terms of our picture exactly that we do have this boundary is 0, and so it does give us our image right there. The other thing that we can do is we can do those row operations. We didn't need to do the row operations because if I go back here, modding out was really easy because I had the generator and I had the exact same generator, so it was easy to mod out. It's not always so easy to mod out. Sometimes your generators and your relators, they don't look so similar to each other. So one thing you can do, however, is if I do the similar column operations, if I'm doing mod 2, I can do the exact same column operations as row. So whatever column operations I did, I'll do the row operations. So I do the row operations except for, oh, I guess I should have done the row operation and put it down here instead. So I could have done it down into here. This is what I was supposed to do. I'll correct that for next time and get into 0 here and move that and leave this. But at any rate, I could have, I didn't, but I could have done exactly the same row operations and gotten my generators that way, and then I would have gotten the same generators. If you work over the not ZMod 2, but over arbitrary coefficients, then you have to do the plus or minus signs, but it's basically the same thing. You just want to make sure you get the same generators to make it easy to mod out. So if you do matrices, it does work out quite nicely to calculate these things. So that's it for today. To talk about this, here on Monday, we will talk about creating your own homology. You all want to do this because you could get famous doing this. Some possibility. You might see something nobody else has seen. So we will talk about that on Monday. And any questions for today? So then I will see you on Monday.